All right, welcome. Today, we're going to dive into something called Spanning Tree Protocol, or STP. You can think of it as this invisible traffic cop that keeps your network from descending into, well, absolute digital chaos.
So, let's kick things off with a question that probably gives network admins nightmares. Have you ever wondered what just one single misplaced cable can do to an entire office network? Yeah, the answer is not pretty. We're talking a complete and total network meltdown. Picture every light on every switch just blinking like crazy, and not a single email, not a single file can get through. Yikes. Okay, so what is actually happening under the hood here? Let's break down the problem that Spanning Tree Protocol was born to solve, the dreaded Layer 2 loop. A Layer 2 loop. It's pretty much what it sounds like. It's a situation where data packets or frames get trapped in this endless game of hot potato between switches, just bouncing back and forth forever. And this kicks off a really vicious cycle. This spiral into chaos? We call that a broadcast storm. It all starts with one switch sending out a broadcast. The next switch gets it, and just like an echo, sends it right back out, everywhere. Then the first switch does the same thing, and boom, it just amplifies exponentially. The switches get so confused that their address books, their MAC tables, start flapping. They just can't keep track of where anything is anymore. The result? A network that's completely frozen.
So how on earth do we stop this self-inflicted disaster? Well, this is where our hero of the day steps in. Spanning Tree Protocol, STP.
And here's the really brilliant thing about STP. It doesn't make you go around unplugging all your extra cables, the ones you put in for redundancy. Instead, it's smart. It builds a logical, loop-free map of the network and just temporarily blocks any path that could cause a loop. It keeps those links on standby, ready to go as backups.
And this right here, it just shows the difference perfectly. On the left, you've got pure chaos, a looping mess. And on the right, you have a nice, orderly, stable network. See? One path is active, and the other one is blocked, but totally ready to jump in if the main one fails, all thanks to STP.
But wait, how does STP decide which paths get the axe and which ones stay open? It's not just random. It all kicks off with something like a network-wide election. All the switches get together to pick one single boss for the network. We call this boss the root bridge. Now, this election isn't about casting ballots. Nope. It all comes down to a number called the bridge ID, or BID. It's just a combination of two things, a priority value that you can set and the switch's unique MAC address. The rule is dead simple. The switch with the lowest bridge ID wins. That's it. Okay, check this out. This is a perfect example of how that works, especially when there's a tie. Both of these switches have the exact same default priority number. So, who wins? Well, it comes down to the MAC address. Since A comes before B, switch A has the lower MAC address, and bam, it wins the election. It becomes the root bridge. But here's a huge pro tip. You should never let this election happen by accident. Leaving it to chance is super risky. You really don't want some old, slow switch that's been sitting in a dusty closet to become the center of your universe just because it happened to have a low MAC address. Best practice is to always take control. You go in and you manually configure your most powerful central switch, your core switch, to win by giving it a way lower priority value. Basically, you rig the election in your favor.
All right, so the root bridge has been crowned. Now what? Well, now it's time to actually build that loop-free map. And STP does this by assigning very specific roles and states to every single port on every switch in the network.
So here's how it works. First, every non-root switch figures out its absolute best, fastest path to the root bridge. That port gets the title root port. Simple enough? Then, for every chunk of the network, the port that provides the best path away from the root becomes the designated port. And you know what happens to any port that's left over? Any port that would complete a loop? It gets put into a blocked state. It's not dead, just on standby, waiting for its chance to shine if another path goes down. And check this out. Ports don't just flip on like a light switch. To make absolutely sure no temporary loops are created while things are figuring themselves out, they go through this really careful sequence. They start off blocking everything. Then they listen to the STP chatter to understand the layout. Then they learn where devices are by building their MAC tables, and only then, finally, do they start forwarding your actual data. But all this carefulness comes with a price, and that price is speed. With the original, classic version of STP, this whole process, from blocking to forwarding, could take up to 50 seconds. Seriously, in today's world, that is an eternity for your network to be down.
Yeah, so a 50-second delay? Obviously not going to fly. That led to some really important improvements. So let's take a look at how STP has evolved and talk about some critical safety features that you absolutely need to know.
These days, you're pretty much never going to run into that original slow version of STP. That's legacy tech. The modern standard is something called Rapid Spanning Tree Protocol, or RSTP. If classic STP was a steam engine, RSTP is a bullet train. It's way smarter and can get a link back online in just a few seconds, not almost a minute. While there are other flavors out there, RSTP is really the one you'll see the most.
Okay, now if you really want to sound like you know your stuff, say in a job interview, you've got to know these safety features. First up is port fast. You use this on ports that are connected to things like a PC or a printer. It lets them skip that whole long waiting process and come online immediately. Then you have BPDU guard, which is like a bodyguard for those port fast ports. If one of those ports ever gets an STP message, which it shouldn't, BPDU guard shuts the port right down. It stops a rogue switch from messing everything up. And finally, there's root guard. This basically tells a port, hey, you are never allowed to become a path to a new root bridge. It's another layer of protection against someone trying to hijack your network.
Phew! Okay, we have covered a ton of ground. So let's boil all of this down to the key one-liners that are going to make you sound like a total pro.
So if someone in an interview ever asks you what is spanning tree protocol, this is your mic drop answer. It hits all the key points. It solves layer 2 loops, and it does it by electing a root bridge and blocking redundant paths, all while keeping backups ready to go.
And this is probably the #1 rule for actually using STP in the real world. You want a stable, predictable network. And that means you, the engineer, are in charge. You should never, ever let the network just randomly decide its own center of gravity. You force the core switch to be the root. Period.
So there you have it. You now know how to stop the accidental chaos of network loops. But that kind of leads us to the next big question, right? What about the intentional threats? You've protected your network from itself, but how do you protect it from someone plugging in an authorized device? We'll just leave you with that thought for now.